开始吗？Okay, everyone. So today I will give you a very short introduction to this paper. It's called Labrador, which is, I will explain what it means. It's apparently doesn't mean a kind of dog. Okay. And yeah, this is the URI for the paper. You can access it because I will not illustrate all the details, formulas in this, so you can check it by yourself. So, what does this Labrador means? I think we can divide it into some parts. The first part is, I think, is this one, which means it is lattice-based. What does it mean? Actually, it's not too important about lattice. Of course, it is post-quantum, right? Like every lattice-based system has this feature, which it means it's post-quantum, but I will not talk about that. And the lattice-based means the computational assumption, hardness assumption, is actually based on something called module cis, which is kind of like is this one? Given a public matrix A, and you get some secret witness S, which is a vector, matrix multiplied by a vector, and the equation is like AS equals to 0, and you want to calculate the S from this equation. It's simple, right? Because everyone can solve the linear system of equation, right? But there's a additional requirement about this S, which is some norm of it is some norm, which means like the length or something like that. Like the L2 norm is smaller than some constant beta, which means this S vector is short, right? So when you, we will exclude the trivial solution, which is S not equal to 0 itself. So that's a kind of cis problem, which can be reduced to some more fundamental lattice problem, and which we can assume that this is the hard problem we rely on. So, and how does this relate to Labrador? Is we will use something called a Johnson. What can I call it? Johnson-Lensen-Strauss, whatever, lemma, which basically means if we project some data point in a high-dimensional space with a random matrix, and the result of it, of course, is the data point can be mapped into some lower dimensional space. But the operation of this projection can roughly preserve the norm, which means it's the distance. Like if you're in some higher dimensional space, your 2 points are close enough, and after this projection into some lower space, the projected 2 points are also roughly closed. Yeah. So we can use these things to reduce the size we want to prove in the Labrador to reach this norm bound requirement. Yeah, but it itself doesn't only used in this lattice-based zero-knowledge proof system, but also I think whenever you want to reduce some higher dimensional data into some lower dimensional data while preserving the distance metric, you can use this JL lemma. So I think it's also used in some machine learning project research, right? Because to reduce the dimensionality of your data. So it's basically, it's just some random matrix, which means the item of it are just sampled from like -1, 0, 1 space, very small space with this is a matrix, and the output is a lower dimensional space, something like that, and the column is the original data, like ND, something like that. And we can apply this projection matrix into some original weightless polynomial vector, and to sum them up to get a projected vector P. And like the verifier will send this ij to the prover, right? And the prover will send this projected P to the verifier. So the verifier now can only need to check like the norm of P is not greater than something like square root of 1 to 8 of beta. Like originally we want to check directly is not greater than beta, right? So by applying the JL lemma, we can only use this check. This is roughly the same with the original, except this constant factor related to the security parameter. Like in general is square root of lambda. Lambda maybe equals to 128. So that's a lattice-based thing. So I think, let me write it on. What is this R? R basically, it means, oh yeah, it's recursive. Recursive, let me write all of it. This A means, I think there are two things of this A. Maybe the first one is aggregated. And second meaning is amortized. And the DOR means demonstration of R1CS. So this R is R1CS. So the demonstration of R1CS basically just means the proof of knowledge of this R1CS relation, right? So POK means proof of knowledge. It's just the demonstration. So it's just a POK system about some relation which can be reduced into R1CS, but itself is called I think it's DPCS. DP means dot product, right? So I will write it out. Basically, we just need, this is a system for proving knowledge of some DPCS relation. So what is DPCS relation look like? It's just like I will write it out. Some function from 1 to maybe 1 to big K. So there's a small k, and it's the one component of it. And we have many S1 to SR. Each of them is a vector of polynomial. So these things are our witness vector, right? So, and we need to have some constraint over this witness vector, which is this function will illustrate. The first part of the constraint is a quadratic part. SISG, quadratic part. And the second part is a linear part. Some phi I SR. And the last part is just the constant part, B, K. Right. So we need this constraint, actually all of the K constraint equals to 0. Okay. And another thing is just this sigma Si. I think it's a norm square. The sum of the norm square of it do not greater than some bound beta square, right? So it is also a constraint system related to the short vector, because we're in the lattice realm. So this is the DPCS constraint system, and I think in chapter 6 of the paper, it's used the entirely chapter to prove the DPCS constraint system can be reduced to R1CS system. So you can check it out, which means this proof system can also be support the popular R1CS. And yeah, so let's say this recursive part. Recursive basically is similar to some protocol you are already familiar with, like the bulletproof. As a BP is bulletproof. O fry or sum check, or NOVA folding scheme. All of them just use this recursively structure, which means like you want to prove some relation, like the instance and the witness belongs to this relation, and you run a protocol like this one, a public concurrent protocol. If it is public on this, the verifier, all of the verifier messages should be a challenge message. And the classical Sigma protocol, the last one of this message should be open of this first commit round, right? And this is challenge. And the recursively structure basically means we won't open this message in hash. Just don't be hasty. Like in this, the message of this open round, we can see it as a witness of another relation, right? Like this is omega prime of x prime with some another relation. So we just to run another similar like protocol to prove this relation. But the point here is this omega prime should be smaller than the original message if you directly send, right? And the recursively basically means you can see this last round message also as a newer relation, and you just to run some smaller protocol to prove this newer relation until you are satisfied with the length or the scale of your problem. And so in the last round, you just send some very small thing, right? And this structure appeared in all of these protocols, and I think it can be abstracted into some thing called reduction of knowledge framework. It's a framework to prove this kind of abstract structure in a very modular way. I think it's a paper apparent in Crypto 23 last year. And I think some newer folding scheme after this this paper, nearly all of them are used this ROK framework to analyze their secure. Yeah. Labrador also has this recursive structure. And we will go into this aggregated part. Basically, it will be divided into two parts. The first part is You, yeah. The first part, basically, you need to aggregate the witness by the commitment of your witness, which is aggregate commitment. Like, if we will commit each of this witness vector Si, right? So we will commit each of this vector by this. This is just it's called a tie commitment, and it's also here also called an inner commitment because it will have an outer commitment, right? Just after it. Why? Because if we only use outer commitment, the commitment of outer, I think, is for each of them, it will be like something like that. What for each of them? 4 KB. So it's still very large, right? So we need some outer commitment to aggregate each of the commitments. So how to do it? It's just we will write this Ti as just decompose it into, I think, many parts, just like the decomposition into some binary decomposition. But here it's just a 哦，明白。Just decompose this Ti into many parts over some basis B1. Yeah, it's B1, right? To divide it into this T1 part. T1 is just some parameter. And we just concatenate each of these coefficients over this base into some new vector called T. T is just to concatenate all of this Ti, right? Concatenate. And we just use another anti-commitment over this T to get this U1, which is we called the outer commitment. OUT, outer commitment. I think it's the first outer commitment. And the prover will send this outer commitment because this one is just 4 KB, right? Exactly around 4 KB, no matter how many parts you divide it. So that's the aggregation of the commitment. And like this one. I will also aggregate the constraint system constraint system also. I think how to write? Oh, it's just like you using some random linear combination over this aij phi a and bk, something like aij will be equal to sigma k alpha k, which is the coefficient over aij k, right? So aij k will be using random linear combination to get this aij, and it will be same we will get phi I and b, right? So the aggregated constraint will be something like this one, S1 to SR. Ij, Aij. Phi I. Yeah, this aggregated constraint just the aggregated of each constraint. So the goal of our system will be reduced to, we want to prove this aggregate constraint is equal to 0, right? So that's the aggregated part. And the last part will be this amortized part, which means we will amortize our working load into each of the weightless vector.或者我现在不用测，连过来。It's amortized part. Just not to directly open this S1 to SR directly, we just to ask for other challenge vector C1 to the CR from the verifier. And each of the C should be drawn from some C space, which is when you when you're programming, it's just I forgot about it, but just like 6640 and 32.1 and 16.2. And space is just something like that, and you will draw from it to sample from it to generate your challenge things. So the amortized just means the prover will send this Z to the verifier. This Z is just the random linear combination of by this C into this SI sigma. Right, so what we can say the verifier can, how many things verifier need to check? No. I think, firstly, directly related to this one, he will check AZ, whether AZ equals to sigma CITI. No. Yeah, it's right, TI. Right. So I'll write it as the first thing the verifier need to check. That's one, right? Okay. And yeah, let me see how to explain this thing. The goal of us is to prove this constraint, the aggregate constraint, right? And we need, which can be reduced to something like this. G, I, J. I will explain what J means. And H, I, and I will explain what HI means. Plus B equals to 0. And so the second thing the verifier need to check is this equation. And we also need to check this one equal to GIJ. And this one equals to HIJ. And I will write what GIJ and HIJ means. Yeah. Yeah, it's just if you are running honestly, the GIJ should be equal to SI and SJ, their dot product. Which means this is also a thing we need to check, right? This thing, the third one. And this thing is the fourth one, right? If you run the protocol honestly, the prover just to cite this called the garbage polynomial into this dot product of the quadratic term and the linear term of your witness vector.
So actually this
yeah, but how does it know this?
Can I ask a question?
Yeah.
Is this formula is just the aggregation of that one, that corner? So you have a lot of constraints.
Which one?
I mean, this equation is the aggregation of this, right? So
exactly.
K constraints.
This is the aggregated constraint. Yeah.
Okay. So what problems this try to solve?
It's a constraint system of your proof system.
But why you aggregate them? Well, why you don't just do this?
To reduce the process.
Okay. So later you'll explain how to reduce the proof size?
No, I think the aggregated part is, the goal of the aggregate part is just to reduce the proof size.
How do you reduce that?
Like, if you don't aggregate them all together, you need to, I think, prove them one by one. It's just like the batched proof of them by using some random linear combination of this each coefficient into one, right?
Okay.
So you just need to prove this aggregate constraint. So you prove your original constraint. And yeah, it's okay. And so how does the verifier know this GIG and HII? Actually, we need to commit to both of them. Also in this message by using another anti-commitment, which is CJ plus DH. G and H is just all of this GIG and HII, the vector of all of them. So we'll call this U2 the second outer commitment. This U2. And the prover will also send this U2 as a commitment. And later on, if you are in your last message, you will open this U2 by sending G and H. So the verifier will know this G and H. And he will check the second check, right? And I think
That's D.
D.
D is
Second outer commitment.
Second order.
D.
C, D, and just another matrix when you are using R-time commitment, like this A, like this B.
Just random select.
No, I think it's there's some requirements when you are using R-time commitment. You can check it.
So A, B, C, D are all
Public the parameter. Yeah, and I think no, 1, 2, 3, 4. Actually, it cannot be directly to verify this. It's verify this by this sigma G I G C I C G by verifying this, and to verify this equation, it will verify this. HIGCICG. So that's actually verification equation used by the verifier.
How do you get these two equations?
Like if this one equals to this one, the Z is just this vector, right? So you dot product by itself, it should be something like that. If J is equal to this. Let me think. Which part? The first one. And the Wi-Fi also need to check the open of this relation are also right. So this would be the fifth verification equation. And the open of this one, U2, need also be checked. So this is the sixth equation need to check. So basically the Wi-Fi need to check this sixth equation. And I think like this thing I explained is just a single iteration round of this recursively structure. You get it? It's basically something I illustrated here. If you are running the protocol just have one iteration, it's just to run all of the steps and you finish. And if you recursively run it, so the last round of your message should be reduced to another smaller relation, and it again a relation into this DPCS constraint system, but to some smaller witness vector. So you will be again recursively run your protocol until the end. Okay, I think that's all of the procedure of how the Labrador proof system works, and you can check each part by yourself, and you can also talk with me about some details. I think I leave some details here and about another constraint related to only the constant term of the system. And okay, thank you very much.